But at this point, what I'd like to do is formally welcome Professor Merryn Tawhai for her talk, Digital Breaths, the Benefits of Bioengineering.
Well, it's great to see such a crowd in the middle of the day. This is number 6 out of 10 lectures that I'm giving across the country. So hopefully I've got this all perfected now so that everybody can take away some valuable messages from my talk. So the title, Digital Breaths, the Benefits of Bioengineering. I am an engineer. That is what I've trained as. I'm not a traditional type of engineer. You wouldn't want me touching anything electrical or mechanical, but I do know about biomedical engineering. I know mathematics, physiology, and how to develop mathematical models that simulate structure and function. So that's what I'll be telling you a bit about today within my own research area. I'll also be giving you some background about the Medical Technologies Centre of Research Excellence, or the MidTech Core for short, and really trying to give you examples of the collaborative nature of this core and why that is of great advantage, or will be of great advantage to New Zealand in developing a medtech sector. So firstly, just to look at, well, why do we really need to develop new medical technologies? Don't we have enough devices, enough things to help us in the medtech space? Well, we are facing, both in New Zealand and internationally, some issues that affect our healthcare system. One is the increase in proportion of people who are overweight, including obesity. This is both a developed and developing world problem, affecting both men and women, as you can see here, developed world, developing world, and globally. So it doesn't look like this is going to stop anytime soon. Another challenge is our increasing number of older people, including now those living into much older age. This means that we have an increasing proportion of the population potentially living with chronic disease. But we also have a large proportion of our older folk who are actually living very healthy into much older age. So we'd like to know, well, what can we do to support healthy ageing? And as you will see as I present more of this work, what do we need to do to be able to distinguish ageing effects from age-related disease? Now, both overweight and obesity and increasing age impact our healthcare spend. And here we have the United States at the top as a percentage of GDP. New Zealand is buried somewhere here in the middle. But healthcare spend is increasing globally, and this is not sustainable. It places so much more pressure, particularly on our public health system, and means that people often are denied access to healthcare services. Now, that's partly driven by these issues of increasing obesity and older age, but it's actually also driven by our demand for new medical devices and technologies. So if companies develop a new technology or a new device, and we perceive that to be better than something else that is available to us, then we demand that of our healthcare services. And that also goes for new procedures or new pharmaceutical treatments. And that's regardless of cost. So, of course, companies are driven by wanting to make profit. They are not driven by wanting to do the community a service. So what could we do about it? Well, public health initiatives. We have many at the moment in New Zealand around, you should eat healthily, you should exercise, you should look after yourself, which will, that's going to potentially help us to keep our weight down and help us to live into older age healthily. But even if these public health initiatives were to be effective right now, our healthcare system will still be having to deal with the consequences of people having been overweight. So there will be long-term consequences. This is only a very long-term strategy. We could rely on the development of new drugs. As I said, these are developed by companies, or companies will purchase the license for drugs that might have been developed in an academic institution, and they are driven by profit. New drugs tend to be expensive, and drugs for the respiratory system, which is my area of research, new drugs are few and far between. There's no magic pill either for obesity or for older age. So one option is to develop smart medical technologies that are developed to improve diagnostics. So if we can diagnose disease early, and if we can distinguish older age from age-related disease, then we can make sure that we stratify patients into the appropriate treatment groups. We also want to develop technologies that would allow us to reduce repeat procedures. So, for example, with a hip replacement, making sure that it's done once and it's done well with the appropriate customised device. So, New Zealand has a long history in medical device technologies. So, Colin Murdoch was a prolific inventor, and he invented the plastic disposable syringe, okay, as well as many other inventions, including the animal tranquilizer dart and a raft of other inventions. Now, he was a veterinarian. He was obviously somebody sitting right at the coalface. He saw a need and he invented something to address that need. More recently, we have Fisher & Paykel Healthcare. They are our largest, most successful medical technologies company. Now, Fisher & Paykel Healthcare arose out of a clinician's need. So when people are mechanically ventilated, so somebody in an intensive care unit who is mechanically ventilated, if the air that's supplied to the patient is not heated and humidified, that can cause drying of the airway and the development of infection. So a clinician recognised a need for something to address this, and through collaborating with engineers at Industrial Research Limited, they came up with a solution which eventually led to the products that Fisher & Paykel Healthcare now sell today around the world. So both of those, what they have in common is that link to the end user, that there was a clinical need or veterinarian need. But that end user identified a problem and then collaboration to come up with a solution. So New Zealand has a large number of companies in the medtech space. They do tend to be relatively small, but what you'll see here, this is just a very small selection from our many companies. What you see here is it's not necessarily about devices. So if you think of medical technologies, you probably think of some new machine with bells and whistles on it. And in this modern era, that is actually typically not the case. Often it's about data. It's about analysing data in smart ways. It's about using that data to customise procedures or customising devices, implantable devices for the individual. So New Zealand has companies that are very innovative, working in niche areas and not trying to just replicate what else is being done around the world. But most of these are small companies, and when you've only got 2, 3 or 4 staff, it's very difficult to be doing things like reaching out to potential international partners or assessing whether there is even an international demand for your product. New Zealand medtech companies cannot survive if New Zealand is their only customer. They have to look internationally for customers. But our healthcare system is quite different to, for example, the United States. So if somebody only designs their technology by thinking about the New Zealand system, then it would not be transferable to the US, which was potentially the largest customer, or Europe. So it's really important to understand what the local clinical environment is like. And small companies can really struggle to do that sort of thing. So recognising that as a challenge, several years ago, the Consortium for Medical Device Technologies was established. This involves companies as well as the tech transfer offices from most of our universities across the country. So the CMDT is very much an industry-facing organisation. It's an organisation where our emerging medtech companies can get support from each other, and our larger companies also provide their knowledge and support for these small emerging companies, as well as a group. For example, hosting visits to international sites. So recently to the Texas Medical Center, a group of companies and researchers had a delegation went to the Texas Medical Center to see how we could leverage that connection for our companies to get a bit of a foothold in the United States. And from the CMDT, this then led to the MidTech Core. So 5 of our research universities collaborated, and Callaghan Innovation collaborated on bidding to become a Centre of Research Excellence in Medical Technologies. That was successful, and we have now been running for 3.5 years. So the MidTech Core, this is highly collaborative. So we have excellent research and have for many years had excellent research in our universities focused on medical technologies or technologies that could be transferred to a medical purpose. But a lot of this has occurred in isolation from each other. You know, we are competitive, and that's part of the reason we're good, because if you have a lot of competition, then you are going to foster a very creative and high-performing environment. But working in isolation is not good for a small country that wants to establish and put our effort into establishing one specific sector. So we recognised that we really needed to collaborate, and we probably needed to manipulate some of that collaboration, because collaboration just sometimes doesn't happen spontaneously. So when we established the core, we put various investigators together. So if you happened to be working in imaging, you had to collaborate in our imaging technology platform. If you happened to be working in lungs, like myself and Jeff Chase from the University of Canterbury, then you had to collaborate and come up with some way of working together to produce a useful translational piece of research. Jeff and I had not met. I'm on the far side with my short hair a few years ago, and Jeff is next to me. We hadn't met before the core was established, but we were thrown together and forced to collaborate, and it's been excellent. And that has happened across the core. Now you can see we are in 4 centres: AUT and University of Auckland in the north, Victoria University of Wellington, University of Canterbury and University of Otago, as well as Callaghan Innovation. We have a nice mix of male and female, engineers, clinicians and biologists. So we have clinicians as our end users embedded into our research clusters. So the core has very broad themes. These themes are really just a way for industry and other researchers throughout the country to understand, well, how could they engage with the core? What is it that we're doing in general that they might have an interest in? But where we have our collaborations are in the technology platforms. So these are areas that really are applicable to, broadly applicable across quite a number of research projects. So imaging and scanning, whether I'm interested in the musculoskeletal system or the lungs or the heart, imaging and scanning is of interest to me. And same with all of our other technology platforms. So these are collaborative projects developing the technology behind each of these areas. Now, the flagship projects are where we have focus on a specific organ system or a specific disease. These are areas where our investigators have a long history of research in this area. They will have a portfolio of basic science research funding, international connections, and so on. So this is just bringing these researchers together in these areas. So I'm going to talk to you more about my own research area, which happens to be one of the flagships in the MidTech Core, so that you can see, well, what do we mean by medical technologies that are not devices? So, as I said, I'm not mechanical, electrical. I could not put any components together. So everything I do is within a computer. So, digital breaths. So for me, this is all about mathematics. And it's really nice to see some of the younger people here, and hopefully you will get a whole new perspective on what you can do with maths and physics and biology and a bit of software development thrown in as well. So as well as increasing obesity, increasing age, we have increasing prevalence of respiratory disease. That is partly driven by the increasing age and increasing obesity, but it's also because of other developed world and developing world problems. Increasing pollution, increasing number of children surviving a premature birth. So there are quite a number of factors that are additive for our increasing respiratory disease. One of the problems in this area is around diagnosis. So diagnosing respiratory disease and being specific about that diagnosis is complicated by the poor correlation between imaging and measurements that are made in a pulmonary function testing laboratory. So if you get your lung function tested because you are suspected of having a lung disease, the first thing that you will do is you will do a forced expiration test. So you will breathe in maximally and you will breathe out forcefully and maximally. The volume of air that you exhale in the first 1 second is FEV1, and your total volume you exhale is your forced vital capacity, FVC. Now, those two measurements are essentially the key metrics for deciding whether you have normal or abnormal lung function. And that is really still the cornerstone of respiratory diagnostics. Now, you can probably appreciate that doesn't seem very sophisticated. What volume do we measure when you blow out forcefully? It doesn't tell us whether you have an early stage disease. It's really only useful for when disease is quite advanced. It doesn't tell us whether your disease is located in the upper or lower part of your lungs. And it's also not great for distinguishing between certain diseases. I could take a couple of you here and you could have identical lung function measurements, but if I were to CT scan you, so computed tomography scanning to get an image of the inside of your lung, people who have identical lung function measurements can have quite different appearance of their lung. So some people can look like they have some fibrosis or emphysema and have what appears to be normal lung function measurements. And also the converse, so you can have normal appearing lung tissue and abnormal lung function measurements. So this really complicates that whole area of diagnostics. So to date, there haven't been quantitative tools that can be used to help in this area. So there haven't been structure function models, which I'll explain more about, for us to really address this limitation. So that's what all of my research has been about for the past very long time. The other issue is that normal aging is poorly understood. So when we study the lung, or when the physiologists have studied it in the past, it tends to be the 25-year-old, 75-kilo healthy male. They don't tend to turn up at the hospital, at the doctor, with a lung complaint. So we really need to understand actually who are the people who are most likely to turn up feeling somewhat breathless, and that is going to be our older population. And why are they breathless? Is this normal aging, or is it actually a lung disease? So we've been developing structure-based models. I'll show you what this means. So what we see here in the middle panel is first a slice through the lung from a CT scan. So this is what we get, grayscale images that show slices through your lung as you're lying on your back. We create what are called finite element models from this imaging. What these models are is a description of the geometry. So it's a mathematical description of the shape of the lungs lobes. So you can see that the lung has 3 lobes on the right lung and 2 lobes on the left lung, as well as all of the airways and blood vessels that are inside the lung. So we use some fancy mathematical algorithms to generate our tree-like structures within the lung shape. So we can do that for airways, for arteries, for veins, and we can also do it for human, which is along the top panel, or down the bottom panel we have pig, sheep and sheep. And we've also used the same methods in mouse and rat. On the far side we have our lung shapes, but now lying on your back or lying on your front. Okay, so when you think of breathing, we know that the lung moves around, right? When you breathe, obviously the lung gets bigger as you're breathing in, and you can appreciate that the air flows through the airways. But the way that your lung tissue deforms, the way that it stretches, that it moves, the way that it deforms when you change posture, that is all very important for determining your overall lung function. When I'm standing upright, so here's my upright lung, my lung behaves somewhat like a giant slinky spring. So the bottom, because of gravity and the weight of my lung, the bottom part of my lung is more compressed than the upper part. This means that when I start to breathe in, the bottom of my lung expands more easily. It's like a balloon that's quite deflated. Whereas the upper part of my lung is an already expanded balloon, and it's harder to start filling. This means that when I'm breathing in, I know that my airflow is not distributed uniformly around my lungs. That also changes if there is lung disease. So it's important that we can simulate the effect of lung tissue, how the lung tissue deforms with posture and how it deforms during breathing. So we use basically engineering analysis that historically would have been used to analyse cars or bridges or sort of big engineering structures. We use those to simulate deformation, the mechanics of our very soft deformable lung tissue. So once we've simulated an airway tree and how the lung tissue deforms, we can put those things together to simulate where the air actually flows to in your lungs. So as I mentioned, the airflow is not uniform. We don't get equal amounts of air going to all of the parts of our lungs. So what we do is we embed our airway tree inside that mechanically deforming lung tissue. the elasticity of the lung tissue and the resistance of the airways are both going to influence where the air gets distributed to. So somebody who's asthmatic and having an asthma attack, their airways constrict, the smooth muscle around the airways constricts, and it will reduce the size of the airways, increasing airway resistance, and therefore meaning you would get less airflow through the high resistance airways. Right, so you will get a disturbance to the flow distribution. For those of us who have normal lung function, actually it's the tissue elasticity that really dominates where the air goes to, not so much the airway resistance. So when you think about breathing, you've probably thought about if you've thought at all about it, you would have thought about airways and maybe your lung getting bigger and smaller, but you probably haven't thought about the pulmonary circulation. So this is often overlooked, even the physiologists don't think about it that much, but extremely important, and currently some of the new studies are really showing that it's even more important than we have thought in terms of the development of disease. So the pulmonary circulation, we do the same sorts of things in terms of simulating now where the blood flows to through the arteries and veins. But this is even more complicated than the airways. There are more little details that we have to consider. Gravity has multiple effects on blood. It affects the tiniest little capillaries that run through the walls of our gas exchange surface. It stretches them or allows them to be slightly fatter, and that will affect the amount of blood that can go through them. Gravity also directly has an effect on the weight of the blood. So we have a hydrostatic pressure gradient in our blood vessels, and that also will affect the distribution of blood flow. So we have to take a lot of things into account to be able to simulate blood flow accurately. And this is easily the most sophisticated model that there is internationally for simulating blood flow through the lungs. So now imagine that I've modelled your airways. So I've imaged one of you lovely volunteers from the audience. I've tested your lung function, I've imaged you, I've reconstructed your airway geometry, your vascular geometry, and your lung shape. I've simulated your ventilation distribution, so where the air has flown to. I've simulated your perfusion distribution, so where the blood has gone. What I end up with is essentially a map of the matching of ventilation and perfusion, so air and blood, at your gas exchange units. So we have on the order of about 32,000 pulmonary acini in our lungs, and these contain many more branches inside them, but importantly they are where gas exchange occurs. How effective gas exchange is depends on the matching of air and blood at these little units. So VQ matching, we call it. So in our model, we end up with an estimation of these VQ maps throughout your entire lung. If we know what the ventilation and perfusion is that is delivered to a gas exchange unit, we can then solve some equations to simulate gas exchange. So simulating the transfer of oxygen into the blood and carbon dioxide back out from the blood. We can then sum all of this information up to give us a prediction of your arterial blood gases. So how much oxygen and carbon dioxide do you actually have in your blood? Right, so all of that is actually just a history of, can we do this? Can we actually simulate lung function? And can we simulate how structure affects lung function? But what that gives us is a virtual digital lung. So this gives us a model, a computer-based model with which we can test interventions. We can test the impact of implantable devices in your lung. We can test what happens if we remove blood clots from a lung? Will there be a clinical benefit from various procedures that we could choose to do? We can also use this to test for new image or model-based biomarkers. So really studying when we measure something, what is it actually sensitive to? So if I'm measuring FEV1, that current standard measurement, actually what exactly is it sensitive to and what is it not sensitive to? So I'll give you an example of how we have used this to help us with our understanding of acute pulmonary embolism. So this is when blood clots become lodged in the arteries of the lung. Here we can see in white are some of the blood vessels, both arteries and veins, and red are blood clots. Now this is not even one of the worst cases that we see. So what we've done is we've collaborated with clinicians at Auckland City Hospital and have taken data from subjects who have been diagnosed with this condition. Now what we wanted to do was to see whether we could firstly explain patient variability. So patients can have very different symptoms of breathlessness and chest pain, but very, very different in the degree of symptoms that they have. But they can have the same clot load. So if I was to add up all of the tissue that's peripheral to each of these clots and say 25% of the lung is affected or 40% of the lung is affected, I can have patients who have exactly the same clot burden and really different symptoms. So why is that? And how should we stratify those patients? Are they most at risk if they have a larger clot load or if they have worse symptoms? So who should we stratify into the high and low risk groups? Secondly, we wanted to see whether through this understanding, could we come up with a really simple radiological scoring system that would facilitate this patient stratification? So here we're using our structure-based methods. So this is some imaging from one of our patients. We reconstruct the vessels, so you see the model in here. What we can do is simulate with no blood clots. So for our baseline function, here we have a perfusion distribution in the upright lung, least perfusion at the top and most at the bottom. We now identify the blood clots on the CT imaging, and we can just put them into the model in the right places. And by resimulating perfusion, you can see that now we have big blue patches where the blood flow is very, very low. Now that has an effect on gas exchange. So what we could see from this is, so this QOI, this is saying 45% of the lung is the blood flow is blocked off to it in both of these patients. But they had very different symptoms, very different outcomes. So depending on whether the location and the size of those blood clots, this will determine the symptoms and the potential outcome. So we're able to show with our model that the underlying physiology of this sort of low to high blood flow and low to high ventilation that we have as we go down our lung, that's very important when you are trying to understand differences between patients. So if I block off all of the upper half of my lung, I would have quite a different impact on my gas exchange than if I blocked off the entire lower half of my lung. So if we want to have a new radiological scoring system, because the ones that have been proposed so far don't work, basically. They do a very poor job. So if we want to develop a system, it needs to take into account the underlying physiology of the lung. So what is usually happening and how have the blood clots changed that? So that's ongoing work at the moment. Now, I'll just try to explain this. It takes a little bit of explaining what this graph is about. So along the bottom, we have our arterial oxygen. So the partial pressure of oxygen in the arterial blood, or the decrease in it from normal. And on the other axis, vertically, we have estimated systolic pulmonary artery pressure. So this is an indication of right heart dysfunction. So you've got left and right ventricles in your heart. The left ventricle delivers blood to the body, and it's a high pressure, delivering against a high pressure system. The right ventricle delivers blood to the lungs, and the lungs are usually a low pressure system. So the right ventricle doesn't have to develop very high pressure to pump blood to the lungs, usually. But when there are blood clots in the lungs, the right heart pressure has to increase to deliver enough blood to the lungs. Now that, if it increases too much and too rapidly, that can cause right heart failure. So that is the ultimate risk for these patients, is developing right heart failure, and hence why we would like to stratify them into low risk and high risk groups. So what we found is, if we take our model and we set it up under baseline conditions, so what that means is we make our model breathe at a normal resting rate, and we make its heartbeat, its cardiac output be at a normal rate, and then we put blood clots in. What we find is that the arterial oxygen would go down. That makes sense, right? Things are not working as well as normal. We don't see that clinically because the normal response of the body is to increase the rate at which you breathe and increase your cardiac output to avoid this decrease in oxygen. But if we don't let that happen, what we find is a prediction of the decrease in oxygen that we would have in the blood, that this correlates very strongly with the estimated, essentially, metric for right heart dysfunction. So our model is pointing towards an easily acquired model and image-based biomarker for right heart dysfunction that we can potentially use to assist with stratifying patients. Again, we're working on that now to test that further on larger patient groups. So I mentioned about the aging lung. Now the lung undergoes significant changes with age, from childhood through to early adulthood, where our lung function, so again you see this FEV1 measurement I talked about, this increases up to early adulthood and then declines on average throughout the rest of our adult life. But you'll see that the values for FEV1 are very variable. So there is a large range of FEV1. This is just for women. So men tend to be larger, but there's still, it's quite a large range. Now what we don't know is if you turn up at age 60 and your FEV1 is about here, and I say, well, that's fine. It's about, let's say it's still within 80% of the predicted value for your age and your height and so forth, I'll say you've got normal lung function. But what I don't know is, where did you sit when you were back here? Were you actually up here or were you down here? If you were up here, then I probably would be rather concerned. Whereas if you were here, well, you're just kind of carrying on a natural rate of decline. We're never going to have access to that information. We're not going to be able to measure everybody in their youth and have that in later life. So we need to come up with smart new ways of understanding what is going on in the older lung, how does it differ from the younger lung, if at all, and how can we exploit that knowledge to help us distinguish between normal age-related decline in lung function and the changes that happen because of age-related disease. So some of the things that we have asked first off is, well, actually, is the older lung, is it actually different? Does it look different? If we look at CT imaging, does the older lung actually look different from the younger lung? If you read the literature would suggest that, yes, the older lung is characterised by the appearance of fibrosis and senile emphysema, and that these changes take place, as well as changes in the chest wall. But there's nothing that actually really specifically has, these are descriptions, but there's nothing that has specifically quantified, gone in and analysed what these changes are, and really do they exist. So we wanted to know, well, actually, what is the tissue, what does it do? Does it deform differently? If I put an 80-year-old or a 20-year-old in a CT scanner, should I expect to see differences in the density of their tissue? So if the tissue deforms, it would be downwards, it would be more dense at the bottom than at the top. Should I see differences with age? Because if the answer is yes, then we should use that information when the radiologists are examining imaging from the older lung. Should I see more heterogeneity in an older lung? So this is, heterogeneity is how mixed up is this thing that I'm looking at. And according to the literature, one would get the impression that yes, I should see more heterogeneity. So we tested those two hypotheses. So firstly, the only graph you should really bother about here is this one. So this is height. So this is somebody lying on their back. So this is back to stomach. And we have in green, we have our under 30-year-olds. And in blue, we have our over 60-year-olds. Now, here I've got, so this is density. Increasing from the stomach to the back. This is our end expiration, so after you've breathed out and you're just holding your breath. And this is end inspiration, breathing in maximally and holding your breath. Now the important point here is that there is no difference with age. So for these are healthy, never smoking individuals who have not had any respiratory disease or cardiac disease, and all aged between about 60 to 80 years. And we see no difference between these groups. So what about the heterogeneity? Well, we have two ways that we measure this. So these are just showing two different approaches. Here we have age along the bottom and a metric for heterogeneity up here. And there is no difference. In terms of how mixed up things look, our 20-year-olds are just as mixed up as our 80-year-olds. But if we look at the dependence of heterogeneity on BMI, we actually do see a strong relationship. So your lung is more mixed up looking if you have a higher BMI, which is again leading us into an interesting new area of research to further evaluate this and explain what is going on physiologically to drive that. Okay, so those are two sort of negative results. We don't see differences. So what other differences might we see if we're just looking at imaging? Well, we decided to create a shape model for the lung. So a statistical shape model. Now, if I had ethics approval to image all of you in this room, it'd be lovely, be able to take all of your imaging and use it to supplement our models. But what I could do is I can take all of your information about the shape of your lungs and I can come up with an average shape. And I can describe mathematically how that shape varies. So what is the main way in which shape varies between all of you as a group? And that might be that it's about the sort of the fatness of the lung compared to its height. Or it might be something to do with roundness. or skinniness. So there are ways in which shape will vary. And we just basically use mathematical methods to describe this. So we've got access to a very large database of subjects in the United States that tend to be younger. So they're from age 20 through to some 65-year-olds, but mostly they're clustered between age 20 to 40. And that's an unusual data set. CT imaging does involve some radiation, so typically it's only used for people with a suspected pathology. You wouldn't just go putting a healthy, normal person through CT scanning. So this is a very unique data set that we have access to. We decided, because it was devoid of the older subjects, to conduct a study in Auckland, getting data from subjects aged 50 through to 100 years, obviously because of our interest in the older lung. And to put all of this data together from the younger through to the older to create a shape model for the adult lung, aged 20 through to 90 years in our case. We haven't got the healthy 90 to 100-year-olds yet that we would like. Okay, so what does this tell us? Well, by modelling shape, what we find, so what's interesting, are the ways in which shape vary. So if we look here at these images, these are shapes where we've got an average shape somewhere in the middle here, and then this is -2 standard deviations from that shape, with the first way, the principal way in which shape is different between people. Okay, and then this is 2 standard deviations in the other direction. So what you can see here is the younger lung, with respect to this way in which shape varies, tends to look more rounded and barrel-shaped. The older lung is more sort of triangular or pyramidal. So what can this tell us, and why would we care about this shape? Well, what we can see here is a relationship with age. We actually see clustering, which is a bit unusual for this type of analysis, but we do see this clustering where these are the young people, the under 30-year-olds, and these are everybody over the age of 30. So we get quite a separation in terms of this shape mode. Now that also relates to, once again, here is our measurement, FEV1, and here is its ratio to forced vital capacity. So we have a relationship between shape and these measurements. So as you age, your chest wall remodels. So it becomes a bit stiffer, and you can get a change in the curvature of your spine. And if you are slouched over at a desk or over a cell phone, whatever is causing your poor posture, that is going to influence your chest wall remodeling. So what we essentially see here is the connection between the change in shape of your chest wall, which your lung is always in contact with, so it just adopts the shape of your chest wall. We see the relationship between that chest wall remodeling and your ability to forcefully exhale in 1 second or in total. So we're getting a new relationship between what you can see on imaging and what you can measure in a lung function laboratory. With other shape modes, there's an association with BMI and with the total volume of the lung. So what this actually gives us is, for any of you in the room who are healthy, never smokers, I could take your over 20-year-olds, high school attendees, I could take your age, your gender, your height and weight, and your lung volume, and I could predict quite accurately what the shape of your lung is, including the location of the fissures, which is the boundary between the lobes of your lung. Why I care about that is because age-related diseases tend to affect your upper or lower lobes more than the other. Fibrosis tends to develop in the lower lobes, emphysema tends to develop in the upper lobes. And that will influence the tissue deformation, and it will mean that the fissure moves away from its normal location. So having this definition of the normal shape and the normal fissure location means we now have something that we can compare abnormal or potentially abnormal against. Okay, so I'm going to show you what we've done in this context for idiopathic pulmonary fibrosis. So this is a disease of unknown cause. It's a progressive disease of the lung tissue with a poor median survival. And one of the problems with it is, again, patient stratification. So some patients will decline rapidly, and others will have a stable, gradual rate of decline. If we were able to separate those groups out, then we would know which groups need to go onto a transplant list and which should potentially receive new expensive medications. But currently there's no way to predict who is going to be a rapid or slow decliner. So we've been working with data from people who have been diagnosed with IPF and applying our modelling methods and analysis methods. But here I'm just going to show you what happens when we compare against normal shape. So we work with clinicians at Auckland City Hospital as well as radiologists at the Mayo Clinic who conduct some image analysis for us. So what we see is, so here you see that sort of younger-like shape, and here we have an exaggeration of that older shape, right? So if you look down at this graph in blue, we have our normal, older, healthy subjects. In orange, we have our IPF patients. You can see that there is a tendency for the patients to be over here, which corresponds to this exaggerated older lung shape. And this also is associated with the amount of fibrosis that's in the lung. So the more fibrosis, the more of this exaggerated older lung shape we see. Now, when I started doing this, my PhD students started working on this, we hypothesized that we would see a shape difference. But because fibrosis is essentially pulling in, it's making the lung really stiff, it's not letting that lung tissue nicely pull out. One would think that the effect of having fibrosis in the lower part of your lungs would be to restrict the outwards pull of the chest wall. But we see here that the chest wall is actually quite pulled outwards. This has made us actually flip our thinking on its head, and that fibrosis is actually more of it's a whole body systemic accelerated aging that is impacting on the lung tissue. So lung tissue is always being broken down and remade, and it's when something goes wrong with that process that you can either start to develop emphysema or fibrosis. So we believe that what we are seeing is essentially accelerated aging that is impacting on the lung tissue and starting this terrible process of remodelling. So how can we use this? Well, it gives us some additional diagnostic information, which we then have to test whether we are actually seeing value out of this. And it also gives us something to look at from a scientific point of view about exactly how could the fibrosis develop and be influenced by these changes in chest wall shape. So in summary, our New Zealand MedTech scene has some points of difference from if we look internationally. We have many small companies, we have research excellence in our universities, and we have a huge amount of collaboration. There's a very collaborative, well-connected network. We have clinicians directly within our development teams, within our research teams, so we really are responding to what is a clinical need rather than engineers coming up with a fancy new product and then trying to find what's the problem that my product might actually address. Medical technologies is absolutely not just about devices. It is about smart analysis, and hopefully you can kind of see that through what I've shown you in my own research area. In my research, we've identified, areas where there really are no tools. There are no technologies to assist us in these areas that I've been looking at. There are no quantitative tools that clinicians, radiologists can use to help them to understand these things and therefore add to the diagnostic process. And we have unique world-leading capability in this area. So our research is coming up with new imaging and model-based biomarkers, so potential single numbers that we can get from existing data, and that's really important. The last thing that we need is to be introducing a new test into the clinic. That adds more expense and more time and potentially more distress for patients who are feeling breathless. So if we can get more information out of existing data, then that will be fantastic. And we definitely need to continue to reassess our understanding of the older lung. What I showed you with the lack of differences between young and old, we had selected healthy never smokers. If you think about what radiologists typically see, they are seeing disease. They are being presented with CT scans from people who are suspected of having a lung disease. And so they are not used to seeing very normal, healthy radiology. So it's important that we actually do develop this new understanding so that we know, well, what's the potential for people in older age. Should we be accepting of lung disease, or should we be saying, no, well, actually you can have very normal, healthy lung function? Okay, so thank you for staying and listening.